Welcome, everyone. Ready to dive deep into the world of particle accelerators?
Absolutely.
We're going to explore how these incredible machines went from, like, tabletop experiments to these absolute behemoths.
Yeah, like the Large Hadron Collider.
Exactly. And how they totally revolutionized our understanding of, well, everything. Get ready to explore the unimaginably small.
A realm of subatomic particles.
Yeah. Billions of times smaller than anything you could see, even with, like, the most powerful microscope.
It really is mind-boggling.
So what drives physicists to build these massive machines and just dive headfirst into this subatomic world?
It's all about answering those really fundamental questions about our universe. You know, things like, what gives matter mass? What are the secrets of that, like invisible 96% of the universe that we can't even see? To even start to answer those questions, we had to go way beyond atoms.
Which for the longest time, everyone thought, like, those are the smallest things, right?
Yeah, the smallest possible units of matter. But in the early 20th century, physicists like J.J. Thomson and Ernest Rutherford, they really started peeling back the layers of the atom.
Revealing this whole universe within.
Exactly. Thomson's discovery of the electron back in 1897, that kind of shattered the idea of the atom as like the ultimate smallest thing.
And then, of course, Rutherford, with his gold foil experiment, showed us that atoms have this structure. A tiny, dense nucleus right in the middle.
Orbited by these, like, little electrons.
Yeah. It's amazing how he zeroed in on those tiny little anomalies in his experiments. Led to a huge discovery.
Oh, absolutely. He was known for saying, like, time to go home and think.
Like shutting down the lab at 6 p.m.?
Every day. He knew there was more to uncover. He even said, you know, we need a machine that can give us a copious supply of electrons and atoms.
He was envisioning a machine that could unlock the atom's secrets, basically.
That's it. And his wish was granted, in a way, by two of his own students, John Cockcroft and Ernest Walton.
At the Cavendish Laboratory, right?
Yep. Working under Rutherford, they built the first real particle accelerator. And in 1932, they did something incredible. They split a lithium atom.
Using their accelerator.
Yeah, it was a landmark achievement, the dawn of controlled subatomic particle study, really.
So what did this first accelerator look like? Was it this, like, massive thing taking up a whole room?
You know, surprisingly, no. Cockcroft and Walton's accelerator was pretty compact. But over in America, there was another physicist, Ernest Lawrence, who was already thinking bigger.
I've heard of him. He's the proton merry-go-round guy, right?
That's him, the cyclotron.
I love that name. Proton merry-go-round. How did it actually work?
Lawrence was inspired by the design of a linear accelerator, but he realized that to get the energies he wanted, it would have to be, like, ridiculously long.
Okay, so not practical.
No.
Right.
So he came up with a circular design instead. In 1931, he built his first cyclotron with his student, M. Stanley Livingston. It was so small it could fit in the palm of your hand.
Wow. So particle physics started small.
It did. But the goal was always higher energies. And to get higher energies, you needed bigger cyclotrons.
But they just kept building bigger and bigger.
Yeah, pretty much. Soon, Lawrence's cyclotrons were taking up entire rooms at UC Berkeley. He was obsessed with pushing the limits.
The race was on. But there had to be challenges with building these, like, massive machines, right? How'd they overcome those to get to even higher energies?
Well, that's where a wartime epiphany comes in. One that changed everything.
Okay, I'm intrigued. Tell me about this epiphany.
This is where Edwin McMillan comes in. He was a student of Lawrence's and was working on war-related projects during World War II.
But even in the middle of a war, he's still thinking about these tiny particles.
He couldn't shake it. And right as the war ended in 1945, McMillan had this light bulb moment.
What was it?
He realized cyclotrons had this big limitation, the size of the magnets. As the particles gained energy, they spiraled outwards. And to keep them on track, the magnets had to get bigger and bigger.
I can see how that would be a problem. Eventually, the magnets would be like the size of a house.
Exactly. So McMillan came up with a really elegant solution. Vary the magnetic field strength. Sync it up with the accelerating particles.
So kind of like adjust the magnets as the particles go faster.
Yeah. That way, the particles stay in the same circular path even as they gain energy. No need for those crazy huge magnets.
So it's not about bigger magnets, it's about smarter magnets.
That's it. And this innovation, which he called the synchrotron, was a total game changer.
Smaller magnets, smaller accelerators, less cost.
Exactly. Opened up a whole new world of possibilities for research.
Amazing how a seemingly small tweak can have such a huge impact.
And here's the thing. McMillan wasn't the only one who had this idea.
Really?
A Soviet scientist, Vladimir Veksler, came up with the same concept around the same time, but totally independently.
Wow. Great minds think alike.
It seems that way. So yeah, this really set the stage for a whole new era in particle physics.
The synchrotron was like the turning point.
Yeah, it led to what we now call big science.
Big science, meaning like massive budgets, tons of scientists, machines that are definitely not fitting on a tabletop anymore.
Exactly. Particle accelerators became like the poster children for big science.
And I bet you're going to tell me about one of the first big science accelerators right now, right?
So you know me too well.
Yeah.
It was called the Cosmotron.
The Cosmotron. The name alone sounds impressive.
It was built at Brookhaven National Laboratory in New York, and it was the first large proton synchrotron.
So using Macmillan's synchrotron concept, but on a much larger scale.
Exactly. And it achieved these unheard of energies over 1 GeV.
1 billion electron volts.
Yeah. One of the physicists who worked on it, Ernest Courant, described the day they hit those energies as like a moment of pure exhilaration.
I bet. Pushing the boundaries of what was possible. But knowing physicists, I'm guessing they weren't content to stop there.
You're absolutely right. The quest for higher energies never really ends. And that brings us to another big innovation, strong focusing.
All right, break that down for me. What's strong focusing?
So remember those magnets that steer and focus the particle beam? Courant and his colleagues, they figured out that by arranging the magnets in a specific way, they could get much stronger focusing.
So instead of just bending the beam in one direction, they're like manipulating it in a more dynamic way.
Precisely. This alternating gradient focusing, as they called it, meant they could use much smaller magnets.
Which means smaller accelerators, lower costs.
This was huge. It paved the way for the giants we have today, like the LHC.
Speaking of giant, what about SLEs? The Stanford Linear Accelerator Center, that's another big science institution, right?
Absolutely. Now, a lot of accelerators were focused on smashing protons together, but SLAC had a different goal. They wanted to see what was inside a proton.
Okay, so instead of smashing them, they used protons as targets.
Exactly, and they used electrons as their bullets. To do this, they built a linear accelerator.
Not circular like a synchrotron.
Right, and this thing was massive, 3 kilometers long.
3 kilometers? That's longer than some towns I've been to.
It was a remarkable feat of engineering, and the payoff was huge.
What did they find?
They found quarks, those tiny particles that make up protons and neutrons. It was like using electrons as a superpowered microscope to peer inside the proton.
Incredible. Another win for big science.
It really solidified our understanding of the strong force, one of the fundamental forces of nature.
So we have this drive for higher energies, pushing the boundaries of accelerator design. And then we have SLAC, using these machines to explore the very building blocks of matter. But I'm guessing there were some concerns about the direction big science was heading, especially the cost.
You're right. There was this growing tension. Some people were asking, should we be focusing on research with more immediate, tangible benefits instead? It's a debate that we're still having today.
It's a tough question. Do we fund the risky, potentially revolutionary stuff? Or do we play it safe and go for projects with clear, practical applications?
And that tension really came to a head in the 1990s with the cancellation of the superconducting supercollider.
The SSC, right?
Yep. It was supposed to be the biggest, most powerful accelerator ever.
I know. And then it got canceled. A major blow for American particle physics.
It was. Costs were rising, political priorities were shifting, and in 1993 they just pulled the plug.
Leaving a partially built facility and a lot of disappointed scientists in its wake.
Yeah, it was heartbreaking for a lot of people. Ernest Courant, remember him? He called it a $2 billion hole in the ground.
That's rough. So what happened next? Did the dream of building even bigger accelerators die with the SSC?
Well, the SSC was a huge disappointment for sure. But the quest to understand these tiny particles, it didn't just stop, did it?
Definitely not. I mean, the SSC being canceled did kind of shift the focus in the U.S.
Right.
more towards, practical applications of accelerator technology.
Right.
But the pursuit of fundamental particle physics, that was still going strong, especially in Europe.
So Europe kind of picked up the torch. They did. CERN, the European Organization for Nuclear Research, they were already working on the Large Hadron Collider, the LHC.
The LHC, the most powerful particle accelerator in the world. What's it like? Seriously, paint me a picture.
Okay, so picture this. A 27-kilometer tunnel buried 100 meters underground.
Wow.
And this tunnel, it goes right across the border of France and Switzerland. Inside, there are these two beams of protons racing around at almost the speed of light.
Okay, so not just one beam like the older accelerator.
No, two beams, and they're steered and focused by thousands of these incredibly powerful magnets.
Why two beams? What's the advantage there?
Energy. To create and discover new particles, you need collisions at these crazy high energies. And when you smash two beams together head-on, you get way more energy than if you just had one beam hitting a stationary target.
Kind of like if you think about two cars crashing head-on versus one car hitting a wall, the head-on collision is way more intense.
Exactly. That's a great analogy. And to reach those extreme energies at the LHC, they use superconducting electromagnets. These magnets are chilled to 271 degrees Celsius.
Meted at 271 degrees Celsius. That's colder than outer space.
It is just a couple of degrees above absolute zero. It's pretty amazing, the engineering that goes into this.
I can only imagine. The LHC, it's a huge undertaking. It must take thousands of people to run that thing.
It does. Scientists, engineers, technicians from all over the world. It's a really incredible example of international collaboration.
And all that effort led to the discovery of the Higgs boson in 2012.
Right. The Higgs.
That was huge news. Why was the Higgs boson such a big deal?
Well, for physicists, it was like finding the missing piece of a puzzle. It was the last undiscovered particle predicted by the standard model of particle physics.
The standard model, that's our best current understanding of how particles and forces work. Right?
Yep. And the Higgs boson, it's the particle that's thought to give all other particles their mass.
So it's like the cosmic glue that holds everything together.
You could think of it that way, yeah. Finding the Higgs was a huge victory for particle physics. It was a confirmation of decades of theoretical work.
It's kind of wild to think that these huge, complex machines we're talking about, they're actually confirming ideas that were first thought up, like on a blackboard somewhere.
Yeah, it really shows how theoretical and experimental physics, they go hand in hand.
So now that they found the Higgs, what's next for the LHC? And for particle physics in general? Where do we go from here?
Well, the LHC is still going strong. Still collecting data, searching for new particles, new phenomena, stuff that might be lurking out there beyond the standard model.
So the quest continues.
It does. There are definitely people talking about building an even bigger collider.
Bigger than the LHE. Is that even possible?
They're calling it the Future Circular Collider, the FCC.
I've heard of that.
It would be a monster.
Right.
100 kilometers in circumference. Imagine that.
100 kilometers. But some physicists, they argue we need to shift gears a bit, right? Not just bigger and bigger, but more precise too.
That's a really important point. Some people are saying, look, we found a lot of the particles predicted by the standard model. Now we need to study them in detail, really understand their properties.
Okay, so how do we do that?
Well, one idea is to build what they're calling a Higgs factory.
A Higgs factory? What is that?
It would be a type of electron-positron collider, specifically designed to produce tons of Higgs bosons. That way, we could study them with much greater precision than we can at the LHC.
So it's like sometimes you need a sledgehammer and sometimes you need a scalpel.
Right, exactly. Proton colliders like the LHC, they're great for discovery. You're smashing these protons together, which are made of quarks, so it's like, smashing two bags of marbles together.
Messy.
Very messy. Lots of debris flying everywhere. It's hard to pick out the specific particle you're interested in.
I get it. So electron-positron colliders, they're more like the scalpel.
Exactly. Electrons and positrons, they're fundamental particles not made up of anything smaller. So when they collide, it's a much cleaner, more precise event. Perfect for studying specific particles in detail.
So we've got these giant colliders like the LHC and then these more precise colliders like the proposed Higgs factory. Are there any totally different approaches out there, something that could really change the game?
There is. It's called plasma Wakefield acceleration. It's still pretty cutting edge, but it has the potential to be revolutionary.
Plasma Wakefield acceleration. That sounds pretty sci-fi. How does that work?
It's totally different from traditional accelerators. Instead of using magnets to accelerate the particles, they use a wave in a plasma. The particles basically surf on this wave and get accelerated to very high energies in a very short distance.
Wait, so you're saying we could get the same energies as a kilometer-long accelerator, but in a much smaller space?
That's the goal. It's still early days, but some people think we could eventually shrink a 3-kilometer accelerator down to, the size of a room.
That would be insane. It would totally change the game. Imagine compact accelerators for hospitals, for factories, even portable ones for scientists to take out into the field.
The possibilities are really exciting. It just goes to show when you start trying to understand the universe at its most fundamental level, you never know what kind of amazing technologies you might end up with.
So the future of particle accelerators, it could be both bigger and smaller at the same time. It's really an amazing time to be following this field. We've come so far from those early cyclotrons that could fit in your hand, and there's so much more to come.
Absolutely. It's a really exciting time. Who knows what we'll discover next? New particles, new forces of nature, maybe even a whole new understanding of physics. And along the way, we're sure to find all sorts of new technologies that will benefit everyone. It's the beauty of scientific exploration. You never know where it might lead you.
So true.
Yeah.
Well, I think we've given our listeners plenty to ponder today. From those palm-sized cyclotrons to the massive LHC and now this mind-blowing potential of plasma Wakefield acceleration, it's clear that we're still just beginning to scratch the surface of what's out there. We haven't even talked about dark matter, dark energy.
So many mysteries still to uncover.
Exactly. And as we keep pushing the boundaries of knowledge, who knows what amazing things we'll find. The future of particle physics is bright, and it's full of challenges and opportunities. It's an incredible field to be a part of. And on that note, we'll wrap up this deep dive into the world of particle accelerators. We hope you enjoyed the journey. Maybe you even learned a thing or two along the way. And maybe, just maybe, this has sparked your own curiosity about the universe and the incredible machines we build to explore it. Keep asking those questions and never stop exploring. Until next time, it really makes you think, you know. We started out thinking atoms were like these tiny solid balls, the smallest things in the universe, and now we're talking about quarks and Higgs bosons and like shrinking a 3-kilometer accelerator down to the size of a room.
Yeah, it's amazing what we've learned. A real testament to human curiosity. We just keep pushing further, building these incredible machines to see what's out there.
But it hasn't been easy.
You're right.
Like canceling the SSC, that was a huge setback.
Mm-hmm.
And these big science projects, they cost a lot of money. There's always going to be debate about whether it's worth it.
Yeah, there are always going to be tough decisions about funding. But I think it's important to remember that fundamental research, it often leads to unexpected discoveries, things that end up having a big impact, even if we don't see it right away.
Right. Like those light sources we talked about earlier. They started out as particle accelerators, but now they're being used in so many different fields. Biology, medicine, material science, even archaeology.
Exactly. And who knows what amazing applications we'll find for plasma Wakefield accelerators if we can figure out how to make them small and affordable.
It's kind of mind-blowing, right? The technology we developed to understand the tiniest particles in the universe could end up having a huge impact on our everyday lives.
Absolutely. That's what makes this field so exciting. It's about exploring the universe at its most fundamental level, but it also has the potential to change the world in ways we can't even imagine yet.
So it seems like the future of particle physics, it's going to be a mix of things. We'll probably see even bigger colliders being built, like the FCC, but we'll also see a lot of work on these smaller, more specialized accelerators, especially with new technologies like plasma Wakefield acceleration coming into play.
Yeah, I think that's a good bet. The field is constantly evolving. There's room for all kinds of approaches. At the end of the day, it's all about finding the right tools to answer the big questions. The questions about what the universe is made of, what holds it together, how it all works.
And who knows what we'll find. Maybe new particles, new forces of nature, even a whole new understanding of physics.
The possibilities are endless. And the journey, it's just as exciting as the destination.
Well said. Well, I think that about wraps up our deep dive into the fascinating world of particle accelerators. We've covered a lot of ground today, from those early tabletop experiments to the mind-boggling scale of the LHC, and even the potential of game-changing technologies like plasma Wakefield acceleration. It's been quite a journey.
It has.
And I hope our listeners have enjoyed coming along for the ride. Maybe you even learned a thing or two along the way. Most importantly, I hope this has sparked your own curiosity about the universe and the incredible machines we build to explore it. Keep asking those questions, never stop exploring, and who knows, maybe one of you listening will be the one to make the next big discovery. Until next time.